Welcome. In this video you'll learn Big O notation, the language we use to describe how fast algorithms grow as the input size increases. We'll focus on intuition, visuals, and a few key curve shapes you'll see over and over, like O of 1, O of n, O of n log n, and O of n squared. On the left, you'll see the main ideas. On the right, animated graphs will show how work increases as n, the input size, goes from 1 up to 10,000. By the end, you should be able to look at a piece of code and quickly estimate its Big O time complexity. Big O is about how the amount of work grows as n grows. We ignore constant factors and small differences, and focus on the general trend of the curve. For example, an algorithm that always does about the same amount of work no matter how big n gets is called O of 1, or constant time. One that doubles its work when n doubles is O of n, or linear time. We care most about the worst case behavior, because that tells us how bad things can get. Constant time, O of 1, means the work does not grow with n. On our graph, that looks like a flat horizontal line. Accessing an element by index in an array is typically O of 1. Reading an element takes about the same time whether the array has 100 elements or 10,000. In practice, nothing is perfectly constant, but as long as growth does not depend on n, we treat it as O of 1. Logarithmic time, O of log n, grows very slowly. A classic example is binary search. Each step cuts the search space in half, so the number of steps is the number of times you can divide n by 2 before you get down to 1. On the graph, O of log n starts off increasing, but it quickly flattens. Even when n goes all the way to 10,000, log base 2 of n is only around 14, which is tiny compared to n itself. Linear time, O of n, is what you get when you do a constant amount of work for each element. A simple loop that walks through an array once is O of n. On our graph, we plot work on the vertical axis and n on the horizontal axis. As n increases from 1 to 10,000, the line y equals n rises steadily. If you double n, the height roughly doubles. This straight line is the visual fingerprint of O of n. Many efficient sorting algorithms, like merge sort and heap sort, run in O of n log n time. You can think of this as doing log n work for each of the n items. On the graph, the curve y equals m log n starts out close to the linear line, but it bends upward as n grows. For small inputs, O of n and O of m log n may feel similar, but as n approaches 10,000 and beyond, that extra log n factor becomes noticeable. Quadratic time, O of n squared, comes from a loop inside another loop, where you do work for every pair of elements. A naive sorting algorithm that repeatedly scans the array can be O of n squared. On our graph, the curve y equals n squared rises very quickly. Doubling n multiplies the work by about 4. Once n reaches even a few thousand, an O of n squared algorithm can become painfully slow compared to O of n or O of n log n. Now let's compare these curves on the same axes. Starting from left to right, we see O of 1 as flat, O of log n barely growing, O of n as a steady diagonal, O of n log n bending upward, and O of n squared shooting up fastest. This picture is why algorithm designers try so hard to avoid quadratic or worse behavior on large data. A small constant factor improvement matters, but choosing a better Big O shape can be the difference between instant results and waiting minutes. When you look at code, you can estimate its Big O by counting how many times the core work runs as a function of n. A single loop over n items is usually O of n. A loop nested inside another loop over the same range is O of n squared. A loop that repeatedly halves n, like in binary search, is O of log n. When you have several independent pieces of code, you keep only the dominant term, the one that grows fastest, because that's what controls the curve for large n. To recap, Big O notation describes how your algorithm's work grows with input size. We saw constant, logarithmic, linear, n log n, and quadratic time, and how they look as curves when n ranges up to 10,000. In practice, aim for O of n or O of n log n when you can, and be cautious with O of n squared on large inputs. Use these mental graphs as a quick reality check while designing and reviewing code. With practice, reasoning about Big O will become second nature.